All right, so last time we discussed the stabilization of the regular elliptic part for SL2, and today I would like to start discussing general reductive groups. We won't finish discussing them today, but we'll start. So let's see, so what did we do? So for SL2, we took the regular elliptic part of the trace formula and we wrote it as a sum of a stable distribution, namely the stable version of the regular elliptic part of the trace formula, and together with the sum over, if you like, quadratic extensions of our ground field of stable trace formulas. Well, not the full part of the stable trace formula, but the G regular part. For the torus, the anisotropic torus of SL2 corresponding to this quadratic extension. And of course, would like to do something like this in general, but here are the complications that we're going to face in the general situation. First of all, we have stable conjugacy. It is not the same as conjugacy under some bigger group. Like it was for SO2. For SO2 we had the bigger group GO2, and conjugacy under GO2 realized stable conjugacy. That's not true in general. The next thing is we have to understand what these summands here are going to be. So the unstable part doesn't just come from tori. That is, we'll have to discuss what are endoscopic groups. And once we introduce what endoscopic groups are, we're going to see that H endoscopic group is not a subgroup of G in general. Sometimes it may happen by accident, but unlike the case of SL2, where the summands here were indexed by anisotropic tori, these were subgroups of SL2. Now the summands will be indexed by some smaller dimensional groups, which are not subgroups of G. So what kind of problem does that give us? Well, it's the problem of how to relate. So how then to relate some element in H to some other element in G. We need to do this because we need to somehow relate a function on G to a function on H. And if for this you need to be able to relate elements. And then another complication is that this function that we're going to have, so the function FTE, how did we get it? Well, basically we had a candidate function and we just wanted to know that it has a smooth extension. And we looked at what do we have to do in order to get a smooth extension. We had to put some decorations in order to do this. Here the situation becomes much more complicated because the function is not this function fh. It's not given or suggested to us anymore. And so we need to somehow get to terms with this. And so what does this then entail? Roughly, well, for one, we need to deal with Galois cohomology. For two, well, we have to understand what endoscopic groups are. For three, we need to find a way to relate elements of H to elements of G. This goes under the heading of admissible isomorphisms. And for 4, these are the transfer factors. So these are the kinds of objects we'll be discussing today. All right. So let's begin with stable conjugacy. So last time we discussed the concept of stable conjugacy, not just for SO2, for a more general group. We assumed that the derived group was simply connected. But we can make the definition without assuming that the derived group is simply connected. Namely, definition, delta and delta prime in G of F are stably conjugate if there are 2 things that have to happen. One is, as before, there has to exist an F bar point that conjugates one to the other. But then 2, we have to now account for the fact that the derived group is no longer simply connected. So this thing is going to naturally live in the centralizer of our element delta. This is a little exercise if you'd like. But actually, it has to also live, if we take the semi-simple part of our element delta, so delta is not assumed to be semi-simple, we can take its semi-simple part. Just by the way Jordan decomposition behaves, this element G is going to conjugate the semi-simple part of delta to the semi-simple part of delta prime. And so this element here is going to preserve the semi-simple part of delta prime, but it may not lie in the connected component of that group, and this is what we enforce. So under these 2 assumptions, we say that these 2 elements are stably conjugate. Kottwitz introduced this condition into the definition of stable conjugacy. So of course, if G derived is simply connected, then by work of Steinberg, G delta S is connected. So stable conjugacy is equivalent to F bar conjugacy, like it was in the case of SO2. But in general, it's not. Okay. So in this, say again? At the moment, nothing. I mean, you can make any definition you like, but soon, once you start working with it, you'd start getting into trouble. For example, Galois cohomology behaves very differently for connected or disconnected groups. Okay, so here is a very simple but very useful definition. Delta in G semi-simple is called strongly regular. Not just regular, but strongly regular, if the centralizer G delta is a torus. Okay. Regular would mean that the connected component of the centralizer is a torus, but you want even more, strongly regular, so that the second condition would then be automatic for strong irregular elements. And for strong irregular elements, stable conjugacy is exactly equivalent to F bar conjugacy. Okay, so then say that we have delta and delta prime in G of F, strongly regular, and then pick a G. Strongly regular is the risky dense open condition, just like regular is. Because after you remove the root hyperplanes, you also remove the action of the possible action of the Weil group. But those are only finitely many elements that you need to worry about. All right, so let's assume that these things are strongly regular and stably conjugate. well, let's then pick something that stably conjugates them, such that adds G delta is equal to delta prime. Well, then, of course, conjugation by G, if it sends delta to delta prime, it sends the centralizer of delta to the centralizer of delta prime. This is an isomorphism. And so the following is very easy to check. Namely, first of all, this isomorphism depends only on delta and delta prime, but not on the choice of G. Okay? And it is defined over F. Even though the element G is not an F point, the isomorphism between the two tori it induces is defined over F because of, well, just because that's how it is. I mean, because of this equation, if you like. Okay, so let's give it a name. We call it phi delta delta prime. It's determined only by delta and delta prime. I never said where sigma was. Thank you. Thank you. For all sigma in gamma, which is the Galois group of F bar over F. My F's are all in characteristic 0. You can replace the bar by S if you want it to be positive characteristic. Okay. Secondly, the map sigma goes to G inverse sigma G is a one co-cycle for the action of the Galois group on the centralizer of delta. And its class, which we're going to give a name now, invariant delta delta prime, its cohomology class, is also independent of the choice of G. Just like the isomorphism between T delta and T delta prime, this cohomology class depends only on delta and delta prime. And then finally, the map that sends delta prime to this class invariant is a bijection between the rational classes in the stable class of delta on the one hand, and the following construction in Galois cohomology. You look at the kernel of the natural map from the cohomology of the centralizer to the cohomology of the group. Okay, so this procedure is what replaces in SL2 the action of GO2F on SL2F. All right, so let's do a simple example where G is SL2 so that we connect with what we did last time. Then we have remember the exact sequence. Guess I'm using deltas now instead of gammas. So we had the centralizer in SL2, but we used tilde to denote the centralizer in GO2. That was our notation from yesterday. And then we have the determinant map to GM. And so on F points, what this gives you is, remember this was E1, E cross. The determinant became the norm down to F cross. And then here, that would be, well, H1 Galois T delta, and then it will come to H1 Galois G. Now this is 0, and so this identifies this cohomology set here with F cross modulo norms from E cross. And this was what we used last time. Without using the language of Galois cohomology, we used this set to parameterize the stable versus rational conjugacy. And now we identify it with this. Okay. Sorry? T delta? Oh, I'm sorry. T delta Twiddle. Thank you. Yes. T delta Twiddle. There we go. Well, it's a minor exercise that tori in GL2 or GLN do not have any cohomology because they're induced tori. All right, so that's that. Now, more generally, we can consider what happens when we then don't have strong irregular semisimple elements, although maybe in view of time, I might skip this. There is a similar picture when you take general elements. They don't even have to be semisimple. There is a similar procedure. But it requires the following definition that is going to be useful for later on. G and H algebraic groups and an isomorphism from H to G over F bar is called an inner twist if the following happens. We can consider, let's see which way around do we do this. We can consider the following composition for any element in the Galois group. We can act with the Galois group on G, then we can go over to like this. So we can act with the Galois group on G, go over to H, act there, come back. That's going to be an automorphism of G if this automorphism is an inner automorphism of G. That doesn't have to be the case, but if it is, we call this an inner twist. And then with this, we're going to have the following analog of this procedure. Let me give this the name. This group, let me give it the name G delta star. This is Kottwitz's notation. Then we have the following fact. The isomorphism at G from G delta star to G delta prime star is going to be, is an inner twist. Now, it's not true anymore that it's independent of the choice of G, but it depends on G only up to an element of this quotient, G delta modulo G delta star, an F point, which means that if the derived group is simply connected, so that G delta star and G delta are the same, then this inner twist will be independent of the choice of G, but in the more general case, it's actually not. And then we have this invariant, this element, G inverse sigma G. This is a Galois cocycle in G delta star. And, well, you may want to say that its cohomology class is independent of G. That's also not true. But its class, once you map it from G delta star to G delta, then the class becomes independent. All right, and finally, the set of rational classes in the stable class of delta is in bijection with, well, not just one kernel, but actually the image of the kernel of H1 of G delta star to H1G in the kernel of H1 Galois G delta in H1 Galois G. Okay, so this is the analog of this fact for general elements. All right, so this takes care of problem number 1. We have now a language to discuss stable conjugacy. All right, so let's now we need to discuss the Langlands dual group. And it has come up a few times, so I'm going to be fairly brief. So G, from now on, G is quasi-split for the rest of this lecture. I'm going to discuss endoscopy for quasi-split groups. Next time I will discuss what happens with non-quasi-split groups. So G is quasi-split. Fix a Borel pair, T0, B0. Then from that Borel pair we'll obtain, well, of course we have the character module, the co-character module of the torus, and inside of here we have the root system, inside of here we have the co-root system, and inside of the root system we have the set of simple roots because we have fixed the Borel, and inside of the co-root system we have the set of simple roots. So what we get is a so-called based root datum. You can make sense of what this means in linear algebraic terms. And there is a duality for these things where you just switch. This is another based root datum. All right, and the way reductive groups work is that to this base root datum, we now obtain, conversely, a triple G hat, B0 hat, T0 hat, and we can take it to be a connected reductive group over the complex numbers, although this has somewhat fallen out of fashion lately, and maybe you want to take it over QL bar. I don't know, but we'll take it over C. Together, well, you not only have a base root datum, but the base root datum here is equipped with an action of the Galois group, and of course, once you switch its components, still equipped with an action of the Galois group. The Galois group, the action on the base root datum does not give you an action on G hat. But if you, in addition, extend T0 hat, this Borel pair, to a pinning, where this X alpha hat is a non-zero element in the corresponding simple root space, so this is for all simple roots, then we get an action of the Galois group on G hat, and then we get the L group, which you can take either a semi-direct product with the Galois group or semi-direct product with the Weil group. Okay, now, then here's a construction that is going to be important. So let T in G be a maximal torus. What we're going to get is, we get a canonical G hat conjugacy class of embeddings of the dual group of T hat into the dual group of G hat. And not only is the G hat, well, canonical in particular, and in particular gamma invariant G hat conjugacy class. What does that mean? Well, how does gamma act? If eta is an embedding of T hat into G hat, then sigma eta is the embedding where we have sigma G hat here, composed with eta, composed with sigma T hat inverse. All right, so the Galois group acts on the set of all such embeddings, and we're not claiming that an embedding, a particular embedding is going to be Galois fixed. In fact, that was usually false. What is going to be Galois fixed is the entire G hat conjugacy class. That's what will happen. So how do you get this? Okay, so choose G in G of F bar, which sends T0 to T, and then compose the duo of that, which goes from T hat to T0 hat, with the canonical identification. Now I'm in a little bit of a trouble because I have two meanings of T0 hat. One is the dual group of the dual torus to this torus, and one is this torus. Well, thankfully, they're canonically identified by the construction of the dual group. So here's what I'm going to write with the canonical identification of T0 hat with T0 hat. Sorry? No, the pinning does, so the pinning part of the pinning is irrelevant for this. It was only there to give you a lift of the Galois action. It's just this procedure. By definition, the co-character lattice of this is identified with the character lattice of this. But this at the same time is the definition of the other version of the dual torus. And so, yes. Okay, so this is a useful construction. And so now we get to endoscopic data, which would have been our problem number 2. What do we replace? I've asserted that without explaining to you why. But let me explain without writing. So what choice did I make? I made the choice of, okay, so first of all, everybody agrees that I did get an embedding of T hat into G hat, so that's good. Now, what did I use to do that? I chose a G. I can change my choice of G. How can I change it? Well, I can only change it by multiplying it on this side by an element of the normalizer of T0. In other words, by a Weyl element. Well, but that means that it's the same as if I compose with the Weyl element on this side. But that's the same as if I conjugate by an element in G hat that normalizes that torus. But that is conjugation within G hat. So that tells you that changing my G is the same as composing this with conjugation in G hat. Now, why is it Galois invariant? Well, if I apply Galois to it, all I would do is I'm going to apply Galois to this, but that would give me another G. And so I would land in the same conjugacy class. There is an identification. Well, I mean, of course, this isomorphism, let's say, what am I trying to say? I mean, the identification of T0 hat with T0 hat identifies the Weyl group of T0 hat with the Weyl group of T0 hat. the Weil group, how do I say, the Weil group of T0 in G is canonically identified with the Weil group of T0 hat in G hat. Yes, because both of these, after all, are, you can think of them as concrete Weil groups, normalizer, mod, centralizer, but they're also identified with the abstract Weil groups, which are the automorphisms of the root system generated by reflections. And the root system and a dual root system have canonically isomorphic Weil groups. So this is where this comes from. Okay, so other questions? Sigma eta is defined. This is the definition. Yes. All right, so endoscopic data. These are going to be the answer to question number 2, namely, what do we replace the anisotropic tori of SO2 with? And, well, I'll just give you the definition. I don't know what else to do. An endoscopic, and they're different. See, if it weren't a headache enough, the one thing, there's actually different versions of it. There is endoscopic data, endoscopic triple, endoscopic pairs, and then there is, of course, different relationships between all of them, and up to isomorphism, they're all the same, but anyway, so here's one of those. An endoscopic triple, HS eta, consists of what? One is a quasi-split connected reductive group H. 2 is an embedding eta from H hat into G hat of complex algebraic groups. And 3, an element S in the center of H hat modulo the center of G hat gamma fixed. Now, how can I make this quotient? Well, this embedding allows me to make this quotient. Okay. Subject to a few requirements. All right. So, subject to the following. First of all, eta identifies H hat with the centralizer in G hat of this element S connected component. That is, I can use eta to map S from the center of H into G. There's going to be a semi-simple element there. I can take the centralizer of that semi-simple element and its connected component. And it's clear that I'm going to get a map like this because S is central in H. So it's going to map H to the centralizer of S in G, but I want this to be an isomorphism. Okay. 2 is that it's similar to this construction here, namely the hat G conjugacy class of eta is gamma stable. The action of gamma on eta is exactly the same definition as here, but we're now using sigma h and not sigma t. Otherwise, it's the same thing. And then 3, so by the way, in this definition, F is local or global. And then 3 splits into whether F is local or global. So 1, F local, is going to say that S lifts to a Galois fixed point in the center of H hat. At the moment, it's a Galois fixed point in this quotient, but you'd like to be able, in other words, you can think of it as an element of ZH hat that's not necessarily Galois fixed, but it's Galois fixed up to the center of G hat. You'd like to actually be able to find something that's honestly Galois fixed in the center of H hat. Sorry? That is a very important question. When the group is quasi-split, you don't. When the group is not quasi-split, you do. And so you have to modify the entire definition to accommodate for that. Okay. F global, S lifts to the center of H hat fixed by a local Galois group for all places, but does not necessarily have to lift to a point fixed by the global Galois group. I cannot do it now, but I will so when we discuss how these things are used in the stabilization of a trace formula. Yeah. I will motivate a little later why it doesn't matter which lift we pick. This I can motivate locally, but the global condition will only happen in the 4th lecture. It really, the motivation of this is related to the construction of Langlands' obstruction to F points in adelic conjugacy classes. And if you have to introduce that first and discuss why is it defined the way it is defined, and then this starts making sense. And I'm going to talk about it, yeah. All right. Okay, there is also a definition of isomorphism of endoscopic data, but maybe I'll just skip it. And if you're interested, you can talk to me about it. And then there is also the following important definition. The datum is called elliptic if the center of H hat Galois the connected component of the Galois fixed points of the center of H hat are equal to the same thing for G. That doesn't always have to be true. Okay, let's do at least one example of such things, namely let's reconnect with SL2. So for G equals SL2, well, first of all endoscopic data are elliptic. And have the following form. Okay, so H is T is an anisotropic one-dimensional torus. And then S I can take as an element of T hat gamma fixed. Well, what is T hat gamma fixed? What is T hat to begin with? Well, T hat is just C cross. It's the one-dimensional complex torus. But because it's anisotropic, Galois acts non-trivial, and the only non-trivial action it could do is inversion. So it acts by inverting an element. And the only elements here fixed, so let me do a little -1 as a subscript to indicate that Galois acts by inversion. And of course, the only elements fixed by inversion are 1 or -1, but -1 is the one we take. For otherwise, we're going to violate this condition here. If we take 1, the centralizer of 1 will be all of G hat. And so we're not going to have an isomorphism. And then eta just identifies C cross with the diagonal torus. So let me just say eta of Z is Z1. Okay. Sorry? Because I'm being silly. So how about this? This is just, what I just said was nonsense. Levy's subgroups are, of course, always endoscopic data. So the split torus is an endoscopic data. Now that was just nonsense. Okay. So that was the answer to question number 2. Now we go to question number 3, namely admissible isomorphisms. The trouble is, see, endoscopic data, well, they have a group, the endoscopic group, but in the case of SL2, the endoscopic group was an anisotropic torus, and it could be identified with a maximal torus in G. Well, this group H is not going to be in any natural way a subgroup of G, and there may not be any way at all to put it into G. But the way out of this is to find a way to not put the entire group H into G, but to put any maximal torus of H into G. So torus by torus you can put H into G, but not the whole thing. And that turns out to be enough. And the way to put a torus of H into G, that is what is called an admissible embedding. So this is what we're going to discuss now. All right. And so the admissible isomorphism, so this is going to be the analog of the isomorphism phi delta delta prime between T delta and T delta prime that we introduced earlier when you have two stably conjugate elements. Two stably conjugate, strongly regular semisimple elements gave rise to a canonical isomorphism like this. We're going to generalize this to the case where one element is in G, but the other one is in H. And there will still be a canonical such isomorphism between a torus in H and a torus in G. So here is how this works. Definition. So we're going to take, let TH in H and TG in G be maximal tori. An admissible isomorphism from TH to TG is given as follows. It's given as the composition, is one whose dual is given as a composition. It's one whose dual is given as the following composition. The composition of, first, you can take the dual of this torus and embed it into the dual of G by our construction that may still be here. Construction. Let's call it construction star. So this is by construction star. 2 is eta, which is part of the endoscopic datum. And 3 is the inverse of an isomorphism from T hat G, an embedding from T hat G into G, again given by construction star. So this is what admissible isomorphisms look like. You can embed the dual of TH hat into H hat, the dual of TG hat into G hat, and then you can transport TH hat from H hat into G hat, and then arrange things so that the images of the image of this composition matches the image of that composition, so that you can invert and go back. Now this is what an admissible isomorphism is. All right, and that immediately leads us to a very central notion for the stabilization of the trace formula. You'd like to have a relationship between elements of H and elements of G. And then the definition is a strongly regular semisimple elements gamma in H of F and delta in G of F are called related if there exists an admissible isomorphism between their centralizers, sending the one to the other. Okay, that's what it means for two elements to be related. And then, remark, then phi is uniquely determined by gamma and delta, and, well, will be called phi gamma delta. So that really became the analog of this situation here. there are no rationality. At the moment, the rationality questions are outside of the building. They're peeking through the window somehow. But for example, this definition says, sorry. It's not that it would have been wrong, but the definition can be made purely without any regards to rationality questions. You can just make this definition for an F bar point and a G bar point. However, the rationality question solves itself immediately in the same way it solved itself for stable conjugacy. Namely, another remark, if we have rational points, then this fellow is defined over F. Because it's canonically determined by gamma and delta. So it has no choice. All right. So, oh, and here's another. Right. You can define this, you can define a transfer stable conjugacy using the categorical quotient as well, yes. It comes out to be equivalent to this. Because after all, the concept of an admissible isomorphism goes through this, which identifies the maximal tori of this, of H and G, and then you can form the categorical quotient using the Chevrolet or the Steinberg map using those two tori, and then the one vial group is included in the other, and it's all the same. It's all the same. All right, so here is a theorem that is going to be used later when we stabilize the trace formula. For every maximal torus, sorry, I want to make just one silly definition before we go on, which is, let's take a torus in H, an admissible embedding of the torus into G is nothing more than composing an admissible isomorphism with a torus in G with the inclusion of that torus into G. So it's kind of an empty definition, but it's useful as language. Is the composition of an admissible isomorphism, TH to TG, with the inclusion TG into G. Okay, but now I can write down the theorem, which is very, very useful and very important about the existence of admissible embeddings. Right, so the theorem, essentially due to Steinberg, says for every maximal torus in H, there exists an admissible embedding of TH into G defined over F. I mean, the existence of an admissible embedding period is trivial by the way things are set up, but the fact that you can find one defined over F is a non-trivial thing, and it uses Steinberg's results on rational points in conjugacy classes. No, it's irrelevant. I mean, tori go around between, central quotients. So that's not the problem. But the crucial assumption which we did make is that G is quasi-split. And this is the first time I really use quasi-splitness. I did use it kind of a little bit before that, but not in an essential way. You could get around it. Here you cannot. This is simply false if G is not quasi-split. Okay. So now we come to the discussion of transfer factors. So what were transfer factors there to do? Remember, in the SO2 situation, so in the SO2 situation, we had a naive map, a naive function on our torus defined simply as the kappa orbital integral of a given test function, and our worry was, does this thing extend smoothly to the singular points? Well, it didn't, and then we had to decorate. There was a lambda, and then there was a kappa, and then there was something here, and so forth. And how did we get those constants? Well, we just looked, what are we missing? Why isn't this thing extending smoothly on its own? Well, we're missing a few things. We studied orbital integrals, and we realized what it is we have to do. So transfer factors play the role of these decorations here for general groups. But the difference now, the very serious complication, is that we don't have even an FT naive. It's not given to us so that we can try and see how is it failing to do what it's supposed to do, because now the group is not abelian anymore. And so all we know is what kind of relationship or what kind of properties we want for the orbital integrals of this function, but that does not specify the function itself. So the situation becomes quite a bit more complicated. So the situation is the following. All right. So I first have to introduce a little bit more things. So remember that this lambda here, this lambda depends on an additive character psi. So this is the first thing we need to generalize. So Whittaker datum for G is a G of F conjugacy class of a pair of B and psi, where B in G is a Borel subgroup over F, and psi is a character which satisfies a certain genericity condition, which is easily set verbally. Its restriction to any simple relative root subgroup is supposed to be non-trivial. We need to slightly improve our concept of endoscopic datum. An extended endoscopic datum is a triple just like the endoscopic datum, but we're going to slightly augment the eta from before, where we have a usual endoscopic datum and L eta goes now from the L group of H to the L group of G, extending eta. Okay. And so in this situation, we will be able to compare these do not always exist. But if they don't exist, then you can do a little hocus pocus, and then you're still fine. Yeah. It's a technical and not particularly exciting workaround when they don't exist. So let's just imagine that they do. They do exist quite often. All right. Then, so given a gamma in H of F strongly regular and a delta in G of F strongly regular related, there is a complex number that tells us how they are related, that expresses the relationship they have. Now, I was planning on giving you all the innards of these things, but seeing as how I have 5 minutes, this is not going to happen. Let me just tell you the one crucial property that these things have, and then we'll move on from there. But so the property is the following. If delta prime are stably conjugate, then there is a relationship between the transfer factor for delta and the transfer factor for delta prime. This is the so-called Kappa behavior of the transfer factor. So this is the behavior. So let me explain this briefly. Remember what was this? This was in H1 gamma of T delta. On the other hand, this S here, this element S, was an element in Z hat, ZH hat mod ZG hat gamma. There is a canonical embedding of this into T gamma hat modulo ZG hat gamma. How does this canonical embedding work? Well, there is a canonical conjugacy class of embedding of this into H hat. And once we embed this as a maximal torus into H hat, then this center is automatically there. And this embedding was well defined up to conjugacy in H hat, but the center doesn't care about that conjugacy, and there you go, you have the center in there, perfectly well embedded. But then you have this, yes, and then from here you can go with this admissible fellow here, C, which is an isomorphism between a torus in here and a torus in there. So from here we're going to go to T delta hat modulo ZG hat gamma. And then there is a pairing between this and this, but given by Tate-Nakayama duality. This is the pairing. Now, this is actually not true because I've divided out by this center. So really, the pairing would go between this and the inverse image of that in the simply connected cover of G. However, this invariant lifts to the simply connected cover. So we could lift it and pair. But we could lift it in multiple different ways. Are we going to get different pairings? No, because we assume that the element S lifts to a gamma fixed point in here. But the reason the lift doesn't matter is because the element we're trying to pair itself lifts to the simply connected cover. And so it's a little bit of a tricky thing, but it works itself out. This is where this is. Okay, so this is all I wanted to say about transfer factors, unfortunately. And then what I wanted to finish with is the concept of so I wanted to finish with what I finished with last time for SO2, but I want to now generalize it to arbitrary groups, quasi-split groups. The first thing is the definition. So a test function in G and a test function in H are called matching if the sum of the orbital integrals what am I trying to say? If this equality holds for any f point in H. For any f point in H, we have the stable orbital integral, which we defined last time, and would like it to be expressed in terms of f in this way, where delta runs over conjugacy classes in G. This sum is finite because for almost all conjugacy classes this is going to be 0, regular semisimple. But for finitely many this will be non-zero. And I wanted to make the example of what happens in the case of SL2. I'll just say it verbally. This kappa behavior is going to tell you that in SL2 you have two summands and one comes up with whatever this is, but the other one comes up with a negative of whatever this is, and this is why the kappa orbital integral was a difference between two orbital integral with some decoration in front, which was this thing. Okay, and then once we have this, there is a big theorem that I have to write down. The big theorem is the following. And there are many names here. Langlands, Shellstadt, Kottwitz, Bautz-Pourget, Ngo. I'm terribly, terribly sorry for using one letter for each of those names. But that's just out of time. And I hope I'm not forgetting anybody. I'm probably forgetting. I mean, Hales worked on this as well. And Lamont was working with Go in the beginning. Anyhow, okay, then we're really going down a rabbit hole. For any F, there is a matching FH and 2, and this is what I forgot last time. If F is the characteristic function in the p-adic case of a hyperspecial maximal compact, then FH can be taken as the characteristic function like this. Of course, this is a little vague. I mean, of course, G is obviously unramified. You want to assume that H is unramified, and the relationship between them, which is encoded in the datum, is also unramified. Okay. And then finally, let me finish with the spectral conjecture. The spectral conjecture is the following. So let phi from the Weil-Deligne group of F to LG be tempered. Maybe let's take it to H. H, phi H to H be tempered. And then we're going to take phi as the composition of L eta and phi H. Remember, L eta is still here. So this is a diagram that we have. We have a parameter for H, which we compose and get a parameter for G. So we have an L packet for G and an L packet for H. And then we expect to have this character identity okay, where these are certain very specific well-defined constants. Because of time constraints, I don't want to say now what they are, but they are quite important, so I'll say that at the beginning of next time, when then I'll also discuss what happens in a non-quasi-split case. For now, I'll just leave them as complex constants like this, and I'll explain them next time. They are discussed, yeah, I just didn't get to it. Yeah.